My name is Ashley Foreman. This is Lab 3 Black Hole. The purpose of this lab was to find the mass of a black hole using the trajectory of a star and its net force. Then, using this found mass, I found the initial velocity necessary to get close to the black hole for a ship without immediately crashing into the black hole or the planet that it left from and then leaving the system. So the models were entirely computational and based on the gravitational force, and the motion of the star was based on Newton's second law and the velocity and position update formulas. I solved for the black hole mass by rearranging the gravity equation, getting the mass of the black hole equals F net times r squared over gravity constant and the mass of the ship. And the initial conditions: the system is a star, the surroundings is a black hole, the time between the data points is 86,400 seconds, the mass of the star is 2 times 10 to the 30th kilograms, and the seed is A4 at georgiatech.edu. Solving for the mass, I used the equation I found earlier, and it outputted a lot of values, the code, and so I averaged all of them together, giving a average value of 8.41 times 10 to the 33 kilograms. And so the code, I inputted these initial conditions. Momentum is, these formulas are put in, like momentum's m times v, and then dp dt, change of momentum, is equal to F net, and so these are like the perpendicular and parallel components of it. And then here is the arrow scale showing the different components of F net, F perp, and F parallel. And so here's the results. So I got 8.41 times 10 to the 33 kilograms. F net is this orange arrow. F net parallel is the magenta arrow. F net perpendicular is the cyan arrow. And so you can see the full orbit and the ways in which the F net looks. And so what does the rate of change of momentum mean? And what it means is that it's simply the net force. The net force is responsible for the change of momentum according to Newton's second law, as shown here. And so the derivative of momentum is simply F net. And that is shown here. And so when F net is equal to 0, the momentum is constant. When F net's not 0, momentum is changing. And so part 2 of this lab was to calculate the speed necessary for a ship to be able to get close to the black hole, but still enough time to escape. And it had to be less than the speed of light, but greater than the escape speed necessary. And escape speed is v equals the square root of 2gm over r. And so here's the code. This is the black hole's mass is updated here. Then I had to find the r necessary between the black hole and the planet. So I used the planet's position and the black hole's position. Same with the ship and the planet. And then I used the gravity equation to update the gravity forces. Then I could find F net. And then the planet's velocity and planet's position and the ship's position and the ship's velocity were all updated using position update formula from Newton's second law. And then the results: the escape speed was very small, while the speed of light is very large, and so it ended up being a lot closer to the speed of light than the escape speed. And so the speed necessary was 2.7 times 10 to the 8th meters per second, and this allowed the ship to crash only after 47 seconds, so that you could get close, but then hopefully have enough time to escape. So what if you wanted to have something orbit around the black hole? And so the speed required to stay in orbit around the black hole depends on the distance from the black hole and the speed. And so as you get closer to the black hole, you need to go at a faster speed. And so using this attributable force equation, mv squared over r, and the net force, which is the gravity force that I found in the first part of the experiment, which was 8.27724 times 10 to the 28th newtons, I found the speed necessary. And so I used this equation and the mass of the star, or the mass of the star, and then the mass of the ship. I used the mass of the ship, and that's how I found this. And so I got 3.438781 times 10 to the 15th meters per second, which is many times greater than the speed of light as shown here. And so here is the orbit. And it completely orbits, and I got no errors about it hitting the black hole or hitting this planet, so this seems to be a good speed for it. And the only possible errors I could have gotten overall in this whole experiment would have been entirely in the way I entered the code and the way I calculated the different speeds, because it was an entirely computational model.